In this video, we're going to discuss tangents and the derivative at a point. Well, we've already talked about how the average rate of change is related to the slope of a tangent line, and we've discussed a little bit on how that is related to the derivative of a function, but we're going to go ahead and strictly define the derivative of f at a point x naught. So quickly we'll draw a picture to remind us what's going on. So we have some point P here, which is x naught comma f of x naught. And then we have some point Q up here. So we have this secant line, and that point Q is x naught plus h comma f of x naught plus h. And then we look at this triangle here, which gives us our differences along the y and the x direction, respectively. So we have f of x naught plus h minus f of x naught here. And this distance is just some horizontal distance, h. So as we've said before, the slope of the tangent line at P, right, is we take the limit as this average rate of change, as the slope of this secant line, as h goes to 0. Sorry, we take the limit as h goes to 0 of the slopes of these secant lines. So this is the limit as h goes to 0 of f of x naught plus h minus f of x naught, all divided by h. So let's go ahead and define the derivative of f at x naught then. So the derivative of f at x naught, denoted by f prime of x naught. So if we write a prime in here, which just means the derivative of this function f at x naught. And this is f prime of x naught is equal to this slope of the tangent line. So we define our derivative to be the slope of the tangent line. So this is our formula for the derivative of a function f at some point x naught, provided this limit exists. Okay, so if this limit exists, this is how we define our derivative of f. Now, there's a few things to say about that. And that is that, there's a few ways to interpret this statement here. Right? And the first one is, this is the slope of the graph y equal to f of x at x equals x naught. Right? That was our first way to interpret this idea of a derivative. The second is the slope of the tangent line to the curve f of x, y equal to f of x, at x equals x naught. The third is the rate of change of y equal to f of x with respect to x at x equals x naught. What does this mean? This means we have a function y equals f of x, and we want to know what the instantaneous rate of change of that function f is. So what is the instantaneous rate of change of y if x is increasing? And our fourth interpretation of the derivative, or the fourth way to interpret this previous statement, is that it is the derivative. So the derivative denoted by f prime of x naught of f at x equals x naught. So all of these four things are equivalent, and they are all interpretations of taking that limit as h goes to 0 of that average rate of change, which was f of x naught plus h minus f of x naught minus h, right? That's what we wrote here. Okay. All right. So there's one last thing that we'll say in this video, and that's just that I want to do an example. So in this example, we are going to ask the question, what is the rate of change of the area of a circle, which our formula is a is equal to pi r squared, with respect to the radius, when the radius is 3. In other words, our radius is 3 on a circle, and we want to increase the radius of the circle. Then our question is, what is the rate of change, the instantaneous rate of change of the area of that circle as we increase the radius when it is currently at r equal to 3? Well, how do we do that? That is exactly the limit as h goes to 0 of the area function from x naught plus h, or evaluated at x naught plus h, minus the area of function at x naught, all divided by h. Well, what is this? Right, area function is up here, so this is the limit as h goes to 0 of pi times x naught, by the way, was 3 in this problem, so 3 plus h quantity squared minus pi times 3 squared all over h. All right, this is equal to the limit as h goes to 0 of, all right, this is pi times 9 plus 6h plus h squared minus pi times 9 all over h. Pi times 9 and pi times 9 cancel, so we get the limit as h goes to 0 of 6h plus h squared all over h. Well, this is equal to, we can cancel one h out, right? We factor an h out of the numerator, then we can cancel. So this is the limit as h goes to 0. Oops. I left off some pi's. I'm sorry about that. That should have distributed. So we get 6 pi plus h. We'll also get the limit as h goes to 0 of that. 6 pi plus h pi. H goes to 0. So, right, we can just plug this in now that this is a continuous function. So we get 6 pi plus 0 pi is equal to 6 pi. And that is our solution. And that's it. That'll end this video.